Okay, let's talk about this idea of AI that seems to be, well, thinking.
Right.
You've probably seen the buzz, around these newer language models, the ones that give you a whole step-by-step breakdown first.
Yeah, the chain of thought before the actual answer. Models like Claude 3.7 thinking, Gemini thinking, that sort of thing.
Exactly. And the implication is they're doing something closer to real reasoning. They're showing their work.
Mm-hmm. Which sounds great on the surface.
But is it really thinking like we mean it? Or is it something else? That's what we're digging into today. We're doing a deep dive into this really fascinating piece of research that came out recently.
From Apple, right.
Yeah, from Apple. It's called simply The Illusion of Thinking.
And it's a great title because it captures what they were looking into. They wanted to get past the slick demos, beyond the standard benchmarks.
Right.
The researchers were basically asking, okay, what are the real capabilities? And maybe more importantly, the limits of these so-called reasoning models when you actually push them.
And not just looking at the final answer.
No, exactly. They wanted to inspect the whole process, the thinking itself.
Okay, so our mission here, for you listening, is to unpack this Apple paper. We want to look at how they set up their tests, what they actually discovered about how this thinking works under pressure.
Or maybe it doesn't work.
Right. And what it all tells us about the AI systems making headlines.
Right.
We want to give you the key takeaways, simply and clearly.
Think of it like we're peeling back the curtain, using this paper as our guide to see what really happens when these models face specific logical challenges.
Okay, let's get into it. The paper talks about LRMs, large reasoning models.
Right, LRMs. These are basically the state-of-the-art language models that are specifically designed or fine-tuned for tasks that need logical steps, planning, that kind of thing.
And the key feature is that thinking part we mentioned.
Yeah, generating that long chain of thought, sometimes even trying to do a bit of self-correction or reflection before they give you the final output.
The idea being that this helps them tackle trickier problems.
That's the theory, yeah. And often it looks like it works.
But the researchers felt the usual ways of testing them, the standard benchmarks, weren't quite cutting it.
Exactly. I mean, these LRMs do score really well on things like math problems or coding tests, but there's always this nagging question.
Data contamination.
Precisely. Did the model just see tons of similar problems, or maybe even the exact problem, during its training? Is it genuinely reasoning, or is it just recalling a pattern it learned?
Right, like sophisticated pattern matching.
And also, most benchmarks just check if the final answer is right. They don't usually validate every single step the model thought it took to get there.
Okay.
So the Apple team wanted something cleaner, more controlled, where they could check the entire reasoning trace step by step.
Which brings us to their approach. Instead of math problems, they used puzzles.
Yeah, classic logic puzzles. Things like the Tower of Hanoi, checker jumping, river crossing puzzles, blocks world.
Okay, what puzzles? What makes them good for this?
Well, according to the paper, they have some really valuable properties for this kind of research.
Like what?
First off, you can control the difficulty really precisely. Add another disc to Tower of Hanoi, and it gets exponentially harder. Add another person to the river crossing puzzle, same thing.
So you can dial up the complexity bit by bit and see exactly where things break down.
Exactly. You're not guessing about difficulty, you're systematically increasing it. Second, these puzzles are purely rule-based, algorithmic. Meaning you solve them just by applying the rules you're given. You don't need outside knowledge. You don't need facts about the world that might have been in the training data. It gets around that data contamination worry.
Okay. Clean rules, controlled complexity, and you can check the work.
Crucially, yes. Every move in these puzzles changes the state in a clear way. The researchers could take the model's thoughts, its proposed sequence of moves, and run them through a simulator.
To see if each step was actually valid according to the rules.
And whether the sequence as a whole actually solved the puzzle. It allowed for this really rigorous move-by-move validation of the entire process, not just the end result.
That makes a huge difference if you're looking for an illusion. You can see exactly where the magic trick fails.
Pretty much.
So what happened? They took these cutting-edge LRMs, like Claude 3.7 Sonnet Thinking, DeepSeek R1, O3 Mini, and put them through these puzzle gauntlets. What did they find?
Well, the findings were pretty striking. They really challenged the idea that these models have robust, general reasoning skills. The big one is what they called the collapse phenomenon.
Collapse? That sounds bad.
It is. What they saw was that even though these models could handle simpler versions of the puzzles, sometimes quite well, and even though they generated lots of thinking steps, once the puzzle complexity hit a certain threshold, their ability to solve it just vanished. It didn't just get worse, it completely collapsed. Accuracy dropped to 0.
Wow, 0. Not just low, but 0.
0. Like a cliff edge they just couldn't get past. They couldn't generalize the solving strategy to harder versions.
So they couldn't scale their reasoning for these planning tasks.
That's what it looks like. And it wasn't just one puzzle type they saw this collapse happen across different puzzles, although the exact difficulty point varied.
And they also compared these thinking LRMs to standard LLMs without the thinking part, right? That comparison had some twists.
Yeah, this is really interesting. If you look at LRMs and standard LLMs that had similar amounts of training compute, their performance varied quite a bit depending on how hard the puzzle was.
Okay.
So for the really easy versions, the standard LLMs, the ones without the explicit thinking, were actually better, more accurate, and they used fewer tokens, so they were more efficient.
Wait, hang on. Adding the thinking made them worse on easy stuff. That seems backwards.
It does, doesn't it? It sort of suggests that for simple tasks, generating all those extra steps might just add noise or slow things down unnecessarily.
Huh. Okay, so what about medium difficulty?
That's where the LRMs, the thinking models, did show an advantage. In that middle zone, the chain of thought process seemed to help them solve problems that the standard models couldn't quite manage.
Okay, so the thinking helps, but only for a bit.
Exactly, because then you get to the high complexity zone, and there, both types of models just hit that wall, complete collapse.
Both of them.
Both of them. The LRM's thinking might push the wall back a tiny bit further, but it didn't stop the collapse from happening. Neither type could reliably solve the really hard versions.
So the thinking is like a temporary boost, but not a fundamental change.
That's one way to put it. It helps them climb a bit higher, but they still can't get over the top of the wall.
And didn't they find something weird about how much effort the models put in, like how much they thought?
Yes. This was another counterintuitive finding. You'd normally think harder problem, more thinking needed, right? The model should generate more steps, use more tokens, try harder.
Seems logical, yeah.
But they found that as the puzzles got really, really hard right near that collapse point, the amount of thinking measured by the tokens used for the reasoning steps actually started to decrease.
It went down,
Yeah.
even though the problem was harder.
Yeah. It's like they just stopped trying as hard or couldn't effectively generate more useful steps, even though they could technically produce more text. They sort of gave up before hitting their token limit.
That feels significant. That inability to ramp up effort when it's most needed, plus the sharp collapse. It points to some kind of basic scaling limit, doesn't it?
It definitely makes the picture more complicated than just more thinking equals better reasoning.
And they also looked inside the thoughts.
Right.
Not just whether they work, but what the steps actually look like.
Yes, and that's where the illusion part really comes into focus. For the simpler problems, they often found the correct solution path quite early in the generated thought process.
Okay.
But then the model would just keep going. It would continue exploring other paths, often incorrect ones, after it had already found the right answer.
Overthinking.
Yeah.
Or just inefficiently wandering around.
Kind of like that, yeah. Then, for the medium complexity problems, the ones where the LRMs had an edge, the correct solution tended to appear much later in the thought trace. It showed they could eventually find it after exploring some wrong turns, suggesting some limited exploration or self-correction.
But not a direct path.
Definitely not. But then, for the high complexity problems where they collapsed, when they looked at the thinking traces, there were just no correct solutions anywhere. The entire thought process was invalid moves, dead ends, flawed logic.
Wow. So it's not just that they failed to finish the puzzle, their internal reasoning process itself completely broke down.
Exactly. It really underlines the inefficiency and the serious limits on their ability to self-correct or stick to valid logical steps when the problem gets tough and requires sustained, precise planning.
The paper also mentioned some specific behaviors that were especially puzzling, right? Like with the Tower of Hanoi algorithm.
Oh yeah, that was a really telling experiment. For Tower of Hanoi, they actually tried giving the model the exact step-by-step algorithm to solve it.
Like telling it exactly what moves to make.
Yep. You'd think, okay, if the model can follow instructions and execute logic, giving it the perfect algorithm should make solving it trivial, right? It doesn't need to figure anything out, just follow the steps.
That sounds like a direct test of its ability to execute precise instructions.
It should be. But what they found was, giving the model the algorithm didn't really help much. Performance didn't significantly improve, and that collapse point, it still happened at roughly the same level of complexity.
Seriously. even when told exactly what to do.
Seriously. It raises big questions about their ability to perform exact computations or consistently follow logical rules, even when those rules are explicitly provided. It's not just about finding the strategy, it seems they struggle with perfectly executing it, too.
Wow. Okay, that's one puzzle. What was the other? Strange behavior.
Inconsistency across different puzzles. The very same model could perform wildly differently depending on the puzzle structure. Okay, take Claude 3.7 Sonnet Thinking again. In Tower of Hanoi, it could actually make a lot of correct moves. Like, for a version needing 31 steps, it might be nearly perfect. For a harder one, maybe the first error doesn't happen until around move 100.
Okay, so it shows some ability for sustained logic there.
It does in that context.
Yeah.
But then you give the same model a river crossing puzzle, even fairly simple versions. It would fail super early, like a puzzle with only 3 pairs of characters needing just 11 moves total. The model might make a mistake by move 4.
Move 4 versus potentially move 100. That's a massive difference.
Huge. And what it strongly suggests is that whatever reasoning capability it has isn't very general. It doesn't transfer well between different types of logical structures.
Maybe you just saw more Tower of Hanoi-like patterns in its training data?
That's the speculation in the paper, that its success might be tied more to familiarity with certain patterns from its training, rather than possessing a truly abstract, flexible reasoning ability that it can apply to any new logical problem.
So the illusion is that it looks like general reasoning, but under the hood, it might be incredibly good pattern matching that works great until it doesn't, until the pattern runs out or the problem type shifts.
That seems to be the core argument emerging from these controlled puzzle tests.
Okay, let's try to sum this up. For you listening, what are the really crucial takeaways from this Apple Illusion of Thinking paper?
I think the main thing is this. These large reasoning models, the ones that show their work, they are definitely powerful, and that thinking process does help them in certain situations, particularly that middle range of difficulty. But they have clear fundamental limits. They hit this sharp collapse point where they completely fail as problems get harder. Their internal thinking isn't always efficient. They can overthink easy stuff. And on hard stuff, the thinking process itself just breaks down.
And the really surprising bits, they struggle to even follow an explicit algorithm perfectly. And their ability varies hugely between different types of logical puzzles.
Right. All of which points away from robust generalized reasoning and maybe more towards that highly sophisticated but brittle pattern matching.
So what does this mean for us when we hear an AI explaining its thought process?
Well, it means we should probably be a bit critical, you know? This research suggests that what looks like deep reasoning might still be hitting fundamental walls when faced with tasks requiring sustained, precise logical execution, even simple puzzles. That thinking we see might be an incredibly convincing simulation based on patterns, but it lacks the underlying robustness to avoid that sudden failure.
Which leaves us with a final thought for you to chew on.
Yeah. If these incredibly powerful models, trained on vast data, struggle and ultimately collapse when dealing with the clear, defined rules of a simple logic puzzle.
What does that really tell us about their ability to reliably reason about the truly complex, messy, ambiguous problems of the real world?
Are we actually seeing the beginnings of general intelligence? Or are we maybe just witnessing a very, very convincing and perhaps quite fragile illusion of thinking?